The next space race won't be one with rockets. It'll be one with nuclear power. NASA is in a high-speed race against China and Russia to build the first compact nuclear plant on the moon, and they want it running by 2030. But this isn't just about energy, it's about control, survival, and staking humanity's claim to the future of space. On today's episode of the Infographic Show, we're looking at NASA's plan to build a nuclear reactor on the moon. If you want to survive on the moon, you can't just pack a few solar panels and call it a day. This is one of the main reasons why NASA is trying to put a nuclear reactor on the lunar surface by 2030. But don't be fooled, the plan isn't just about science, but global power. A lunar day is nothing like an Earth day. One full cycle on the moon lasts about 27.3 Earth days, which is 14 days of blazing sunlight, followed by 14 days of complete darkness. That 2-week-long night is the deal breaker for solar power. Even the most advanced solar arrays paired with high-capacity batteries can't reliably store enough energy to keep life support systems, research labs, and heavy-duty machinery running for that long. Basically, nuclear energy is not just preferred, but an inevitability to make a moon base viable. And that's where NASA's Fission Surface Power System comes in, a small but powerful nuclear reactor designed to churn out at least 40 kilowatts of continuous power. For context, that's enough to run about 33 average U.S. homes, but still tiny compared to a typical onshore wind turbine's 2 to 3 megawatts. What's important when setting up a power plant on the moon is small size and reliability, both of which the Fission Surface Power System has going for it. At least theoretically, it's important to note that no such reactor has actually been built. It's just been shown that it could work on paper. But this isn't just an engineering project, it's a geopolitical sprint. In May 2025, China and Russia announced plans to build their own automated lunar nuclear power station by 2035. And that puts the United States in a high-stakes sprint to plant its flag on the moon's energy future. Sean Duffy, acting NASA administrator under President Donald Trump, wrote in an urgent letter to the agency that it is imperative the agency move quickly to ensure the U.S. leads in this critical technology. In order to do this, NASA will need to solicit proposals from private companies to design, build, and launch a 100-kilowatt reactor by 2030. NASA wants something modular, lightweight, and rugged enough to survive a moon landing, but robust enough to operate for at least 10 years without refueling. That means advanced shielding, autonomous operation, and an almost maintenance-free design, all of which are big asks. But why the rush? Who cares who puts a reactor on the moon first? Well, whoever controls the moon's power grid could control its economy and potentially its strategic value as a deep space launch hub. The moon isn't just a dusty old rock, it's the gateway to Mars, asteroid mining, and possibly a trillion-dollar space economy. But without a dependable power source, none of that can happen. We'll explore the nuances of these factors later in the video, but suffice it to say that many are betting that the moon will be hot real estate in the future. Experts say that with enough funding, it is technically possible to hit the 2030 deadline, but there is a catch. The very administration that wants to achieve these ambitious goals has cut NASA's budget in the past, and it plans on slashing it by 24% in 2026. And that raises questions about how this plan will all come together. Still, the administration has pointed out that small reactor designs already exist, and if the U.S. truly commits the resources, the technology is ready to go. So what are the specific problems that the United States faces when planning to build a nuclear reactor on the moon by 2030? First, there's the issue of simply getting there. The plan is to use the Artemis program to get the reactor there, but as many have pointed out, this just isn't feasible. Right now, the Artemis program is already behind schedule. Artemis 3, the mission meant to return humans to the moon, is slated for 2027, but it's been hit with delays, funding uncertainty, and repeated setbacks. Without a steady stream of crewed and cargo flights, any reactor project is dead on arrival. And even if the rockets are ready, there's the question of what you're actually launching, because sending a nuclear reactor into space isn't like ordering a new TV off Amazon. The main concern for many is launching radioactive material into our atmosphere. If something goes wrong and the rocket explodes, radioactive particles could rain down on the planet below. Obviously, this would have catastrophic environmental and political consequences. Then there's the fact that the geopolitical aspect of the mission could backfire. Some scientists have warned that it seems like we're going back into the old first space race against the Soviet Union. Unfortunately, this can lead to missions being launched too soon or science itself taking a backseat to bragging rights. Which brings us to the less than stellar track record of space missions during this time in history. The United States has only managed to land astronauts on the moon 6 times, all between 1969 and 1972 during the Apollo program. Back then, we used the Saturn V rocket, which is ironically still the most powerful rocket ever flown for missions. But the Saturn V hasn't been built in over 50 years, and nothing in operation today matches its proven capability for moon missions. Even if Artemis gets up to speed, the logistics of building a moon base are nightmarish. The International Space Station is just 250 miles away, yet it took over a decade and dozens of assembly flights to complete. The moon is almost 239,000 miles away, meaning each trip would take about 3 days and require massive amounts of fuel. The carbon footprint of dozens of moon cargo runs could be significant, adding yet another layer of environmental debate. Life support is another puzzle to the complexities of getting a reactor up and running on the moon. Astronauts and engineers would need to be present to construct and troubleshoot the reactor, which means there would need to be a pretty sizable moon base. The base would need food, breathable air, and a stable power supply while the reactor is being built for months at a time. While hydroponics and other experiments aboard the ISS have shown promise, scaling that up for a moon base under reduced gravity and constant radiation exposure has never been done. Some engineers want to build the base out of lunar concrete, a mix of moon dust and cement, rather than just haul everything from the Earth. While early tests show this concoction might be stronger than many Earth materials, the technology is still experimental. Even if they build the shelter on the moon, the critical parts for the reactor, control systems, shielding, heat radiators, would all still have to be launched from home. And then there are the landers. Right now, there is no fully operational independent lunar lander capable of delivering heavy cargo safely to the moon. SpaceX's Starship is a candidate, but multiple test flights have ended in explosions. Blue Origin's Blue Moon lander is also in development, but neither has yet demonstrated the safety record that you would want before loading hundreds of kilograms of uranium and then launching it over populated areas. Technically, both landers are expected to be operational by 2030. But the truth is, there is absolutely zero margin for error. Any setback, such as a delayed rocket, a failed test, or a political budget cut, could push the project past the deadline. And as mentioned before, nuclear reactors are not the kind of thing you want to rush into space. So while the dream of powering the moon with nuclear energy is scientifically sound, the path to getting there by 2030 is littered with engineering challenges, safety hurdles, political landmines, and technological unknowns. In short, NASA can do it, but only if everything goes perfectly. And space history tells us it rarely does. Now let's focus on the reactor itself. In January 2024, NASA completed the first phase of its fission surface power project. Several private companies proved it's possible to build nuclear power systems that are safe, clean, and reliable, at least on paper. 3 contracts were extended to gather more data before Phase 2, where the plan is to develop a working unit, test it for 1 year, and then operate it for 9. And this all sounds reasonable, until you realize Sean Duffy is pushing for a 60-day consultation to greenlight a design that would need to be ready for a launch date in 2030. In engineering terms, 5 years is the blink of an eye for something that must operate without a single catastrophic fault. Even if the lander touched down on December 31st, 2030, that is still an incredibly short development cycle for a brand new space reactor. NASA has some prior experience, however. The kilopower reactor using Stirling technology, better known as Krusty, proved robust in ground tests. It used uranium fuel rods to produce heat, and then it melted sodium inside of heat pipes. The heat transferred to a gas that drove the Stirling engine piston, producing electricity. Krusty is simple, reliable, and able to generate a few kilowatts. The current fission surface power designs scale up that using a closed Brayton cycle power conversion system, where uranium decay heats a working fluid that spins a turbine. The problem is that these systems still waste a lot of heat. The new goal is to minimize heat loss and push efficiency higher, but increasing power means increasing complexity. And this is where things get even crazier. Duffy is no longer asking for 40 kilowatts like the original proposals. He wants 100 kilowatts. That's a 150% increase over early specs without a proportional increase in development time. Then there is the mass problem. NASA originally wanted the reactor to weigh no more than 13,000 pounds, so it could fit on a standard launch vehicle. In spaceflight, mass equals money. More mass equals higher launch costs, and in this case, the reactor also has to survive a gentle lunar landing. Cooling is even a bigger hurdle. On Earth, reactors use billions of liters of water to carry away the heat. The moon doesn't have oceans or rivers. Sure, there is ice in deep craters, but how much and how easy it is to mine remains a mystery. Space reactors are smaller, so the cooling problem is technically more manageable, but it's still critical. Without cooling, you don't just lose efficiency, you risk meltdown. Krusty avoided this with passive cooling, which is when the heat from uranium decay melts sodium in the pipes, and the system carries the heat away without pumps or complex moving parts. And that's fine for a few kilowatts. But scaling that up to 100 kilowatts? That could require much more sodium or entirely new cooling fluids. If the material has to come from the Earth, that makes the reactor heavier, driving up launch costs. If it has to come from the Moon, you're suddenly talking about building mining and processing facilities before you can even power the base. Every design choice has to be locked in, tested, space qualified, and ready to fly in just 5 years. That's 5 years to invent, scale it, certify it, and deliver a one-of-a-kind machine. That has to work flawlessly in one of the harshest environments in human history. If you're gonna bet your entire moon base's survival on one piece of equipment, you probably don't want to rush it. Now let's go into a little more depth about the real reasons why the United States government wants to put a nuclear reactor on the moon. When NASA talks about putting a reactor on the moon, the public hears clean energy and scientific progress, but behind the press releases is a very different reality. This isn't just about powering habitats, it's about securing territory, building influence, and shaping the rules of the next great frontier. A 100-kilowatt reactor could do far more than keep the lights on in a lunar habitat. It could power rovers to explore thousands of kilometers without recharging. It could run life support systems indefinitely, and it could even help generate liquid hydrogen and oxygen from lunar ice to fuel missions to Mars and beyond. Once that kind of infrastructure exists, a permanent human presence becomes not just possible but inevitable. And with permanence comes territory. Under the Artemis Accords signed in 2020 by 8 nations, countries can establish so-called safety zones around their operations on the moon. Officially, these zones are there to protect equipment and ensure safety. But as some have pointed out, that looks an awful lot like saying, we own this bit of the moon and you can't come near it. And that's where geopolitics comes in. According to Politico, acting NASA Administrator Sean Duffy has repeatedly warned that China and Russia could use the same rules to carve out prime real estate. Duffy's own words go even further. He wants the United States to claim the, quote, best part of the moon. And in his view, best means a very specific area near the lunar South Pole where permanently shadowed craters are thought to hold vast deposits of water ice. Water ice isn't just for drinking. Split into hydrogen and oxygen, it becomes rocket fuel. Whoever controls that fuel source could control interplanetary travel, creating a lunar refueling hub for missions to Mars and beyond. And that's why Duffy's statement, "We have ice there, we have sunlight there, we want to get there first and claim that for America," isn't just about science, it's about strategic dominance. The South Polar region also holds another advantage. Parts of its ridgelines receive near constant sunlight, ideal for solar arrays. But the richest craters lie in permanent darkness, where solar power is useless. And that's why nuclear reactors are the perfect strategic tool. They let astronauts, rovers, and drills operate where the sun literally never shines, bringing energy independence to the moon's most resource-rich terrain. But there is a legal wrinkle. The 1967 Outer Space Treaty says no nation can own land in space. Yet safety zones create a loophole. If you have a nuclear reactor on the surface, you can legally restrict access around it for safety reasons. That means without technically violating the treaty, you can establish a de facto zone of control. Whoever gets there first gets to decide where those zones are and how big they'll be. So yes, NASA's reactor will be about energy, but it'll also be about claiming ground before rivals can, locking in control of the moon's most valuable resources, and cementing the United States as the primary power in the solar system's first off-world economy. With all this talk of racing back to the moon to place a nuclear reactor and exclusionary zones, it's worth noting what a future moon base might be used for. A permanent moon base wouldn't just be about surviving on the moon, it would be humanity's first true interplanetary gas station and workshop. Launching from the Earth is expensive, really expensive. It costs around $10,000 per pound to send material into orbit from our planet's deep gravity well. But the moon's gravity is just 16.5% of the Earth's, which means rockets leaving the moon need far less fuel to escape into deep space. And that opens the door for a revolutionary shift in exploration strategy. Instead of building and fueling deep space ships on Earth, we could assemble them on the moon, launch from there, and save billions. NASA's Lunar Reconnaissance Orbiter has identified potentially 600 million tons of water ice in permanently shadowed craters near the moon's poles. As we mentioned before, this water can be split into hydrogen and oxygen, the same propellants used in some of the most powerful rockets ever built. With a large enough processing plant, a moon base could produce thousands of tons of propellant per year, turning it into the refueling hub of the inner solar system. From there, Mars becomes a much easier target. A spacecraft fueled on the moon could reach the red planet in 6 to 10 months depending on the launch window, without the heavy fuel burden of an Earth launch. And it doesn't stop at Mars. The same infrastructure could send robotic or crewed missions to the asteroid belt, home to trillions of dollars in raw materials, or even to the icy moons of Jupiter and Saturn. Think of the moon base as a cosmic pit stop. It could be a place to repair ships, swap out crews, refuel, and launch ambitious missions that would be prohibitively expensive from the Earth. And if humanity ever dreams of sending a generation ship or advanced probe to another star system, the moon could be the logical departure point. Not only would it allow for massive assembled-in space vessels that could never survive a launch from the Earth, but it would also reduce costs and risks to levels that make the impossible possible. A lunar base also offers a stable platform for telescopes and sensors far from the Earth's atmosphere and radio interference. Imagine radio telescopes placed on the moon's far side that are shielded from all human-made signals and able to study the early universe in wavelengths that Earth's noisy airwaves block completely. This could revolutionize astronomy in the same way the Hubble Space Telescope transformed our view of space in the 1990s. And let's not ignore the military and geopolitical implications. Even though the 1967 Outer Space Treaty bans weapons of mass destruction in space, a permanent moon presence means surveillance platforms, communications hubs, and rapid response launch sites that could all be positioned 239,000 miles from the Earth, well outside of conventional reach. Whoever controls that infrastructure controls critical space highways for decades to come. And then, of course, there is tourism. Yes, it sounds like science fiction, but with companies like SpaceX and Blue Origin already developing lunar landers, the first wealthy tourists could set foot on the moon within the next 15 years. And eventually, all of those space tourists are going to want a place to stay, which would require some kind of moon hotel. Over time, tourism revenue could even help offset the staggering costs of lunar infrastructure. But here's the catch. Every single one of those ambitions, from mining ice to powering a boutique hotel on the moon, depends on one thing: power. And the moon is a brutal place to keep the lights on. And that's why experts are saying long-term lunar survival isn't just a challenge, it's an engineering nightmare. Power isn't just for lights and heating, it's for running life support systems. Without a reliable round-the-clock power source, all the high-tech habitats, laboratories, and mining rigs in the world are nothing more than very expensive frozen sculptures. If the reactor works, it could be the backbone of every moon base to come and the key to turning the moon from a barren rock into humanity's first true space colony. With rival powers fast on their heels, the stakes have never been higher, and this is a race for the future of human civilization. When that small nuclear reactor lights up on the moon's surface, it won't just be a power source, it'll be a beacon of what we can achieve when science, technology, and determination collide. The next giant leap isn't just about going to the moon, it's about staying there and reaching far beyond. If NASA can power a lunar base with a nuclear reactor, could Mars be next? Watch The Real Problem with Living on Mars to see why surviving there might be far harder than you think. Or click on this video instead.